All right, today we're going to discuss the power of transposes and symmetric matrices. This is slightly more theoretical than I would have liked, but it should be straightforward nonetheless. And today we're going to focus on symmetric matrices. So what is a symmetric matrix? So a matrix is going to be symmetric if it's symmetric about the diagonal. So one example of this might be our favorite identity matrix. That's nice and symmetric about the diagonal. So you can fold it across the diagonal as symmetric, right? But it doesn't have to be the identity. You can come up with any sort of matrix you want as long as it's symmetric. Right? And here, it doesn't have to have bands on the diagonal either. So notice that these are symmetric. Those ones are symmetric, even though the diagonal is different. So as long as you can fold it across here, it's symmetric. And the main thing about today is kind of understanding why we really care about symmetric matrices, and it has to do with transposes. So algebraically, a matrix is symmetric if A equals A transpose. So if you swap the rows and the columns, then if you get the same matrix, it's going to be symmetric. Another important property about symmetric matrices, or another consequence of this also means that the entries Aij are going to be equal to Aji for all the entries j and I. So you can just swap the indices and you'll get the same thing. This may not seem like a big deal, but what we're going to do for the rest of today is figure out what does this mean geometrically. So kind of algebraically, it's just crunchy numbers. It's its own transpose. But what we want to figure out is what does this actually mean geometrically? And there's two very main properties that this is going to induce. Right? And it has to do with transposes. And actually, this is true for any matrix, not just symmetric matrices, but the consequence comes down a lot to symmetric matrices. So for any matrix, A doesn't have to be symmetric. We have that the kernel of A transpose is equal to the image of A perpendicular. So this here on the left, this is the set of solutions to A transpose X equals 0. And this on the right are all vectors Y perpendicular to any vector, to all vectors AX. So these are going to be the same thing. And the key thing why we care about this in the context of symmetric matrices is that what does this say for a symmetric matrix? This says that for a symmetric matrix, the kernel of A is equal to the image of A perpendicular. Or more precisely, this just says the kernel is perpendicular to the image. So when you've been doing these before and after graphs, a lot of times the kernel and the image, they're in different graphs. But for symmetric square matrices, those are going to be in the same space. So maybe we just do a quick example of this. So let's just consider the matrix. Let's just do this one right here. That's a nice and symmetric matrix. And we kind of know what this does. This is going to project and stretch onto a certain line. So this one's going to do this. It's going to go onto the line 1, 1. And same thing with that green vector. And if we take this blue vector right here, that's going to get squashed down to nothing. So the kernel of this matrix looks like this. That's where the kernel is. So this right here is the kernel. This is the kernel of this matrix. And the image of this matrix is going to be right here on this line here on the right. And both of these are in R2 because this goes from R2 to R2. And you'll notice very specifically, because this is symmetric, if in fact you overlay these, they're in fact perpendicular. So this is an example of why we care about this. Sorry, this is the image, and those two spaces are perpendicular. So the perpendicular space to the image is the kernel and vice versa, but only specifically for symmetric matrices. All right, so let's explain. Let's prove. Let's prove this fact, that the kernel of A transpose is equal to, that's a transpose. A transpose is equal to the image of A perpendicular. And this may seem strange, but this uses just the understanding of what the kernel, image, perpendicular, and transpose really mean. All right, so if we have A transpose X equals to 0, this means that X is in the kernel. That's what this means. So if X is in the kernel, that just means that A transpose X is equal to 0. This, we can multiply both sides by Y. So we're going to multiply both sides by Y transpose. So this is something we're allowed to do. All right, and now this on the right is just a number. As is 0. So if we take the transpose of both sides, that's still going to be just 0. And now we're going to apply the property of transpose. So when you transpose, you're going to flip everything back and forth, and you're going to apply the transpose to all of them. So then we're going to get X transpose AY equals 0. And now this says that, now if we look at this, we're going to associate it like this with the AY. Well, AY, for any Y, this is the image of A. And here, this says that X is in fact perpendicular to that. All right, and then since AY is anything in the possible image, X is perpendicular to everything in the image of A. And that's precisely what we get when we go up here. So these are just kind of connecting a lot of the dots, and all of these steps go backwards as well. So if you start with the image, you can go back to the kernel. So this is just a key fact that we're going to leverage later, but the kernel and the image are related when it comes to transposes. All right, there's another key fact that's important that we're going to leverage, and it uses kind of the same. All right, so now we're going to jump to another fun fact. So this fun fact says that the kernel of a transpose is related even further to the kernel of the matrix. More specifically, what this says is that applying A transpose after A can't affect the kernel. All right, so let's just do a quick example. See this in action. Let's go ahead and take the matrix 0, 1, 0, 0. And so this is going to be our A. So what does this matrix do? It's going to take these two vectors, and we'll take this one, take those three vectors, and it's going to take the red one, the 1, 0 vector, to, that one gets squashed rather. The green one's going to go to 1, 0, so 0, 1 to 1, 0. And say this other one, minus 1, 1. That one's also going to go to 1, 0. All right, and now, so the kernel of this is going to be everything that gets squashed. Everything that gets squashed is going to be follow on this line. So everything on this line is going to get squashed to here, to the first one. Everything gets squashed. And now the question is, do more things get squashed if we apply A transpose? So we apply A transpose, right? Is it possible that more things get squashed? Well, the answer is going to be no, because when we apply it again, these vectors are just going to remain right where they are. No more things get squashed as a result, but all those vectors still stick with where they are. So the amount of squashing that happens from here to here is the same amount of squashing that happens from one end to the other. It's going to be the same, you get the same result, and that means the kernel doesn't grow. The kernel is the same for A as it is for the total process, and that total process, keep in mind, is A transpose times A. So this is kind of a geometric picture showing that the kernel doesn't grow after applying A transpose, after applying A. And why is this true? So why does this work? Well, we're going to connect some of the dots from before. So if we have A transpose AX equals 0, this right here, this means that X is in the kernel of A transpose A. These mean the same thing. All right, but also, we also have, if that's true, that AX is in the kernel of just A transpose. From before, this means that AX is in the kernel, sorry, in the image from before is in the image of A, but perpendicular to the image of A. But on the other hand, by the definition, this is just the definition of AX, is in the image of A itself, because it's a product, it's a result of what you get by multiplying by A. So it's in the image of A. And the only way you can get these two things together if something is perpendicular to itself. So the only vector that's perpendicular to itself is the 0 vector. And this implies, by the definition of the kernel, that X is in the kernel of A. So we started with the fact that X is in the kernel of A transpose A, and we concluded that X is in the kernel of A. And many of these steps go backwards in the same manner. So we get that our fun fact is true for any matrix A, not just symmetric matrices. For any square matrix A. Oh, sorry, for any matrix, not just square. That's for any matrix A. So this is kind of a simple idea. You can apply the techniques and apply transposes. Let's just do let's cool down with a nice simple application of this. Let's check to see if something's symmetric. Right, so keep in mind the definition is a matrix is symmetric if A equals A transpose. So let's suppose we take any matrix B. So is B plus B transpose symmetric for any matrix B? For any square matrix. That's important here. So is this going to be true for any square matrix B? So what we're going to do is we want to check this condition. We want to check, does this matrix equal its transpose? Does A plus B transpose? When you transpose it, what do we get? So what we're going to do is we're going to just apply the transpose. And this T distributes over addition for transposes. That's the same thing as just flipping the rows and columns of B and flipping the rows and columns of B transpose. So we're going to get B transpose plus B transpose transpose. This just means flip and flip back. So that's just B over there. And this, of course, you can commute the matrices when you add them. And so, yes, this is symmetric because you get what you started with when you take the transpose. So that's a nice, easy way to check if a matrix is symmetric without necessarily knowing the contents of those matrices. All right, so all together today, we kind of looked at the geometric properties and the algebraic properties of symmetric matrices and their transposes. The key thing to keep in mind is what a symmetric matrix is. So a symmetric matrix A equals A transpose. And you have these nice fun facts that geometrically, the symmetric matrices have the kernel and the images align in a very perpendicular manner. And that, as a consequence, tells us that if you apply A transpose, that you can't zero out any more than you already have with A.